So, okay, we're going to start we're going to go back and work on chapter 3 a little bit. So last time we kind of finished up application problems for first order equations. And next thing here, we're just one section in chapter 3. Section 3.1 is called Euler's method. It's like a numerical method, okay, for finding a solution to a differential equation. Okay, and basically, idea here. Let me kind of draw, like, say you have xy axis here like this. Okay, you have a differential equation, first order. But so say dy dx equals some function of x and y over here, like this. And normally, so far, we've had functions over here. We tried to solve it. Maybe it's separable or a linear or Bernoulli or something like that. But it could be in general over here. It may not be one of those special kinds of equations. It may not be exact or whatever. But it turns out you can still get like a numerical approximation of what the curve looks like for a solution curve. So basically, the situation is here. You have a differential equation, okay, and you have some initial condition like this, okay? And basically, the way Euler's method works, you start at, if I try to explain it here, so let's say you start your point here, x naught, y naught. So let's say, like, here's x naught, y naught, like right here. I'll try to label it, say x naught, y naught. Okay, so you start at this point right here, okay? You know that. And what you do then, for Euler's method, I remember we talked about the slope field, right? You found slope fields before, where we plotted them out. Okay, if you put in the value of x and y here, you can get the slope field at that point. You can get the little section line there, the slope field line. So you evaluate the slope field here at this x naught, y naught. It gives you like a little thing like this here then, like the little slope field element, like that. Okay, and basically the idea of Euler's method, you pretend this becomes like a line here for a little bit. So you take this and you kind of extend it. Okay, so you march along a line here. Okay, and maybe there's some step size here then. Like say this is like x naught, and maybe you go over here a little ways, and then you stop here. It's like a tangent line here, or like a line here. Okay, and then that puts you to the point here, like x1, y1, say right here then. Okay, and there might be like a step size h here. So you'd have some step size like this. So you basically find your slope field element here. Pretend it's like for a little bit, at least, you draw the tangent line here, and go this, extend that little element out, extend it further out over some step size here. And that puts you at some point here then. Okay, and then you do the same thing. Now you plug this in back over here, okay, and you get like the slope field element there. So now you'll get maybe something like this, like a little element there, okay, and then you extend that out a little bit, say to x2 now. This is like h again. This is like the step size. So step size h here. Okay, now you're at a point here. This is x sub 2 comma y sub 2. Okay, and if you keep doing this here, right, eventually you get something that kind of looks like the solution curve, supposedly. Like, you make an approximation, right? Like you got a little line like this, and these little polygon. You get like kind of like a polygon. These little line segments here. You get a line here, and then a line here, and then a line here, and it gets better. It's pretty crude, but if you make the step size small enough, you do pretty good with it. So if you don't get too greedy here with the step size, okay, you can actually get a nice plot of the curve then, the solution curve. But it really depends on what the step size is. Okay, if that kind of makes sense. Okay, so and basically here's it's like an algorithm. Okay, here's what it is then. So this is Euler's method. Okay, it goes like this. X sub I plus 1 is equal to x sub I plus h. That's just the step size. Okay, and then the y here, y sub I plus 1, okay, is equal to y sub I plus, and then basically it's the step size here. Take the step size times the slope, okay, times the slope there. That's f evaluated at x sub I comma y sub I. Like that. So this is like your original y here, and then this is like the delta y. It's like the change in the y here. So if you take your step size and then multiply by the slope here, like that. Okay, and this is it right here. This is a pretty simple method, actually. This is called Euler's method. Okay, to approximate a solution. Okay, to the differential equation here. Okay, so anything on that so far? We'll go through an example, see how it runs, how it works here then. That's the idea. Okay. And this part here, this might kind of make sense here. I think this makes sense here, right? You're just going by the step size here for the h. This part down here, kind of a way to look at it. Don't write this down. But you think of like this is kind of like the slope right here, right? This is the slope. If you think of it as like kind of like delta y over delta x, like this, and then the h is like the delta x. So, this is like your slope right here. And then you have your delta x, or your step size here. That's this. Basically, let's cancel, and this is your delta y. So you have your original y here, plus this is like the change in the y, okay, if you go along like this line. Okay, so that's where that kind of comes from there. Okay, so just to see how it works then here, let's say we have this. Let's say we got dy dx is equal to x minus y. So we have this differential equation, and we have this initial condition here, y of 2 is equal to 3. Okay, and let's say the step size, we'll use h equals 0.1. So that's like the step size here then. Okay, so basically the way this works here then, you just kind of make like a little, I'll show it like this. So you have your x naught, your x sub 0 would be what? That would be the 2, and your y sub 0 would be 3. Right? So that's the initial point on the solution curve right there, 2, 3. Now x sub 1, so you go to 1 here. And what is x sub 1? That is equal to basically from this here, right? So x sub 0 was what? That was 2. So basically it goes like this, and x sub 1 would be 2 plus, what's the h? The 0.1, right? So 2, so it'd be like this. Or in other words, 2.1. So that'd be x sub 1, and it'd be 2.1. Okay. And then y sub 1 would be equal to y sub 0, which would be 3, plus the step size, which is the 0.1, 0.1, times the function, that's this thing here, right? Evaluated at these numbers up here, the x sub I, y sub I, 2, 3, like that. Okay, so then you crunch this out here. Okay, so that's like, you go through that, that's 3 plus, and then, f evaluated at 2, 3. You put in 2 here, put in 3, x and y, right? So you get like -1. So this guy's -1 right here. So you get like -0.1 when you do that. And it comes out to be, I guess it would be 2.9 you would get. So that'd be your y sub 1 then. Okay, anything else so far? Now if you want to keep going then, right, your x sub 2, that'd be what now? That'd be basically now that'd be 2.2. You basically add 0.1 again from the previous one. That's 2. Well, I'll just write it once, but it's pretty obvious, I think, for this. But right, that'd be 2.2 here then. So it's the previous one plus 0.1. Okay, and then now the y sub 2 is equal to what? It's the previous y value, which was 2.9, plus, and then step size times, then function evaluated at, now the previous ones here, 2.1, 2.9, like this. So you go through that calculation here. So you evaluate the function back up here at 2.1 and 2.9, for x and y, and that comes out to be, it's 2.82 is this one. Any questions so far? How this is going? This? Okay. Now I'll do one more here. Say x sub 3. Okay, that would be 2.3 now. Then y sub 3 would be 2.82 plus, and that 0.1 times the function evaluated at, now the previous one here, that'd be 2.2, 2.82. Okay, and I'll just tell you the answer here. Again, that's just putting it back up here for the x minus y. Okay, you go through that. These are numbers I got anyway. I don't know if it means, if you're doing this or not, that's okay. But if they may get a different number if they tried it. Hopefully these are numbers you're getting if you're doing this. But it should be about 2 point, it should be this one here. And then so on and so forth. Okay, so you kind of march along then. And these x, y ordered pairs, and there's a supposedly points should be near the solution curve then. Okay, going along there. So any questions on that? So that's the Euler's method. Okay, that's pretty much all there is to it. Now, one thing I want to show you then, I want to actually graph it out here. Or one thing to mention too, the actual solution here, okay, is you can actually find the actual solution. This is actually a linear equation here, if you go through it. Okay, so actually you could solve this, right? So you could solve this initial value problem because this is just a linear equation. Okay, so if you want to get the actual solution, it turns out it's this. I'll just write this down here. Okay, that's the actual solution. You can get it because it's a linear equation. You can actually solve it. So we solved this like in the first test. We solved things like this, right? So we had this one here. But just for comparison, let me go ahead and graph these together. I'll plot these points in the actual solution just to see how it's doing on it. Okay, so let me try that here. Stop sharing here. And now I got to go back here. I'm going to just do this in Desmos. So join now. I'll go to Desmos. Okay, so let me share a screen here. And okay, open graphing calculator. So the actual solution is whatever I just said it was there. Can't remember. Okay, so the actual solution is this. It's y equals x minus 1 plus 2 e raised to the negative x plus 2 negative x plus 2 here. Yeah. Oops, I want this in the exponents. I guess I gotta do a parenthesis, I guess. That's 2. Right? That was it there, I said. Okay. So there's the actual solution to the differential equation, that initial value problem. So let's look at Euler's method. So Euler's method then, initially, our initial value is what, 2, 3. So this is the first one here. Okay, so I don't know if you can see that. Okay, so there's the first one. Okay, that was the initial point in the curve, right? And then, now what was the next one in Euler's method? What was next solution? 2.1, thanks, and 2.9. There's the next one, the green one you can see. Okay, that's the next one. So it's doing okay so far. Haven't gone very far yet. And then 2.2, 2.82. That's the purple one there. You can kind of see that. It's starting to go off a little bit. It's not quite, And then next one we got was 2.3 and 2.758. That's that one there. So if I zoom in there a little bit, you can see the further you go, the worse it's going to get. Okay, this is already starting to lose some here. Okay, but if you made step size smaller, you could do better, right? I use 0.1 for step size. If you make step size smaller, then it's more calculation, okay, but it'll start getting us more closely a little bit. But it'll still veer off eventually, okay? So anyway, you can make it better for smaller step size. But basically, that's Euler's method, okay, there for getting a differential equation. There's actually better methods. There's one called Runge-Kutta method. They talk about it in the book, but it's more calculations involved in it, especially if you do it by hand. Okay, but on computer, if you put it in a computer like on Maple or something, it'll use a different method. It's better than this. The same basic idea, but it does better though. Get some other methods. And so, okay. So anyway, anything on that? Okay, so that's Euler's method. That's what I have to say about Euler's method. And so,
will it say like
how many times to go? Yeah, on the homework it'll say like find like y sub 3 or something, or it might tell you the step size and say it'll tell you the step size and then you can figure out how far to go that way too. Yeah, there'll be some on the homework that'll tell you how far to go. So.
Doesn't Euler have like Euler's numbers?
Euler has everything, pretty much. Euler's number, the E. Yeah, that's Euler's. Yeah.
And there's also the other Euler's number.
There's yeah, the gold from the there's a bunch of Euler's. There's also an Euler's equation, the E I theta. Yeah. But yeah, there's lots of different Euler's numbers out there. So, but okay. So anything there on that? Let's see. Okay. Let's see. Yeah. Okay. So next thing here then. Let's see. Yeah, that's the end of that chapter. So we're done with that. So back here. Okay, so next thing then, let me switch back here then. Let's see. Share screen. All right, so it's the actual solution there. Okay. Oh, yeah. Next thing here, then let me switch back. Show you something else. Oh, I'm still back on this. Wait a minute. Back here. Okay. So handout here for you real quick before we start the next chapter. So kind of a handout here. We'll go over this quickly, kind of quickly. But I have a handout for you. Thank you. Okay. This is kind of some background stuff for the next chapter. Basically, we're going to start like second order. So we're done with first order now. We're going to start second order. That's like second derivative. Okay, so we're going to start looking at equations now. We're just like y double prime and then stuff in these. Okay, and kind of start off here, just a little bit of background. We'll get some problems in a minute. But this is kind of go over the sheet here a little bit. This is kind of, they talk about this in the book, like actually in section 5.1, but just a little bit of background stuff here. So let's see. Okay, so let me check here. So if anybody has a question, if you can get in the chat, somebody's online here on this, I think. But if you can put it in the chat, maybe I can take a look at it. So okay. So anyway, so here then, yeah. So it's a little bit of background here. If you have this is called a second order linear equation here, like this. Okay, so second order linear, it's homogeneous because there's a zero over here. But basically for now, if you have an equation like this, okay, it's like y double prime and then a function of x here equals 0. Okay. Suppose it has, say, two solutions here, like y1 and y2. Okay. It's also true then, right? If it has two solutions like this here, the sum of these here with constants in front is also a solution. So if I know, say, here's one solution to the equation, here's a different solution, okay, then this is also a solution here. If you add them together and put constants in front. And this is kind of the proof of it if you go through it. Basically, if you take this and substitute it in, substitute in here. The idea is here, the second derivative, these derivatives, right? When you take derivatives, it's like a linear thing, right? So you can take derivative term by term. So and there was the sum of this. If you have the second derivative of a sum, that's the same as the sum of the individual pieces here. Okay, so you can go through this, but basically, I just want to point out this happens here. So if you have two solutions here, this is also a solution here then, if you go through it. If you go through this, this is the key part right here. Like, see, this here is the same as this, if you think about it, right? Because if you have a function of x here and a function of x here, you take derivatives term by term. So you can end up taking a derivative like this, okay? And then, like, for example, if you have, like, say, x squared plus x cubed, right? The derivative of this, if you want to find d dx of this, for example, you take the derivatives individually. It's the same as this. Don't write this down, right? Because you can do this. The sum of this derivative of sum is the same as sum of the derivatives. Okay, so basically make use of that here, and you could read through this and look at that. But and then this thing right here, right? This guy right here, then, for example, that is equal to 0, right? Because y sub 1, by we're supposing here, y sub 1 is the solution to this. If I put in y sub 1 here, for example, I get 0. If I put in y sub 2 here, I get 0, because we're assuming these are solutions to this. Okay, so that allows you to get some zeros here. Okay, and then you end up with this right here. That's the bottom line on that one. Okay. And then also to here, the second one, if you have an equation like this here, and these are, let's say y1 and y2 are non-trivial solutions. That means they're not 0. Okay. Because if I can put in 0 for y and get a solution. If I put in 0 for y here, it's a trivial solution. Because you take two derivatives of 0 function, it's still 0. And okay, but anyway, non-trivial solutions. And if the solution is like this, where one's not just a multiple of the other, okay, then it turns out that this guy right here is going to be the general solution, which means all the solutions are contained in this. So if y1 and y2 are like this here, okay, then all the solutions to this problem, okay, are contained in this right here, okay, in this expression. Okay, so, and basically tonight we're just going to be working with these two things here mostly. The rest of the sheet we'll talk about another day, okay, but we're going to work on these here with equal 0. The ones tonight, they're going to be equal to 0 here. They're going to be homogeneous. So, but, okay, anyway, let's just get into an example here. So, I figured it was worth doing a handout for that instead of writing all that down. So it might have been a lot for a handout, but anyway, or for just writing it all down. So we're going to look now at section 5.2. Kind of get started here. So we're going to talk about now homogeneous linear equations with constant coefficients. Okay, is this one here? Okay, so let's see. Okay, so anyway, here's the problem, what they'll look like. So they'll look like this here. Plus cy equals 0. Okay. So all the equations in this section look like this here, where the a, b, and c are constants. Okay, so it's like a special case of that handout. We had like a p of x and a q of x here. Okay, but in general here, that for this one, we're going to assume the a, b, and c are constants in this. Let's say here. Okay. Yeah, and by the way, we won't do it here, but you could divide through by the a here in this. Okay, if you divide through by the a, assuming it's not 0, okay, then this is like your p of x here, and this is the q of x. If you divide through by the a, then it's a special case of on the handout then. Okay, but anyway, we're gonna look at ones like this here, where the constant coefficients, And first problem is here. Let's say we want to find the general solution. GS for general solution, let's say. So y double prime minus 5y prime minus 6y equals 0. So we'll find a general solution here for this. Okay. Now you might remember back on the first test, maybe the first couple of nights, I gave you some solutions. You had to find values of R that made them true. Basically, let me start this here. You want to look for this. I'll start with this. Look for this to start. Look for y equals e to the rx. Okay, so we're going to look for solutions like this here. Okay, we'll just kind of see a shortcut here when we go. But for now, we're just going to look for solutions like this. Okay, so what would I do then? I would plug that in up here, substitute it in. So I would take two derivatives here. What would happen then if I take two derivatives? If I take two derivatives and sub it in, when I sub it in, I take two derivatives, what would I get? So what would be first term here, do you think? If I take two derivatives of this, R is like a constant. So what would be two derivatives then? Yeah, R squared e to the rx. I see R squared e to the rx. That'd be two derivatives there. Minus 5, and then one derivative would be what? That'd be just R e to the rx. From chain rule there you do. Right, so R e to the rx. Okay. Yeah. Yeah. That's okay. A pen, like a pencil. Yeah. Here.
Thank you.
Oh, okay. Okay, and then minus 6y. The y here is y is r. So what's the y here? That's e to the rx equals 0. So looking for solutions like this. We're trying to find basically r here that will make this true. Okay. Now, if I factor out the e to the rx, there's a common factor of e to the rx. You factor out. Let me check something here real quick. Let's see. Oh, there's a quick question online. The handout, it's actually on my open math. So you can get it right off of my open math. So the handout that I gave here tonight. So, okay. So anyway, so you factor out the e to the rx here. So r squared minus 5r minus, I lost the 6 here. My bad. There should be a 6 there. Minus 6 equals 0. Okay. Now, this guy here, no matter what r is, this can never be 0. Right? This is never 0 here. Okay. So the only way this can happen then, right? This will work out here as long as this is 0. If this is 0 here, then the product's 0. Right? So basically here, so must have r squared minus 5r minus 6 equals 0. Like this here. Now look back up here for a minute. We'll solve this in a minute. This guy, you notice it looks a lot like this one up here. You see this up here? It looks like if the coefficients 1, -5, and -6. That's the same thing down here in the R. And this is called the characteristic equation. Okay, so this is called the characteristic characteristic equation. So the characteristic equation here for this. Okay, so basically in future problems, you don't have to do this every time, this part here. You can just look at this and get right down to the characteristic equation here. Okay, even these numbers are different. Different numbers, it still follow the same way. And you get down to here then. Okay, now you solve this here. You can factor it. So that's r minus, r minus 6, r plus 1 equals 0. So that means r equals 6 or r equals -1. Okay, so it looks like here then, for solutions, what we got, y equals y, I'll call it y sub 1. There's two solutions here. Y sub 1 is equal to e to the 6x, and y sub 2, we got another one here, is equal to e to the -1x, like this. Okay, so we got two solutions there. Anything there so far? Now, because we have two solutions here, right, and one's not a multiple of the other, okay, from the handout then, right, that means the general solution would be this. I can say y equals, it's c1 e to the 6x plus c2 e to the negative 1x. Okay, that's the general solution. So all the solutions are in this here. Okay, this has all the solutions to the equation here then. You notice you get two different constants here with this. Okay, so anything on that? So that's the answer there. Okay, so that's the general solution for it. You notice, like unlike the first order cases, actually you actually have two different constants here they can mess around with. Okay, so on that. So okay, another example to try here. Let's say find the general solution. This is how this works. Let's say y double prime plus 4y prime plus 3y equals 0. Like that. Well, basically, all you're going to do here, first you can find the characteristic equation. Okay, so what that'd be r squared plus 4r plus 3 equals 0. So you can just do that right away here. Okay, so then you solve this, so you get this, you can factor it in this case. Say r plus 3 times r plus 1 equals 0. So r equals negative 3, or r equals negative 1. Right, so general solution is this then. Y equals c1 e to the negative 3x plus c2 e to the negative 1x. And that's it. So at this point, it's pretty easy, right? So it's not too bad there. That not bad for a second order equation. You know, for the work you have to do, there's not much to it with the constant coefficients there. Anything on that? Okay. Gets a little trickier though. So anything here? This is nice. It works nice as long as the roots are nice. There's also nice distinct roots. This works nice so far. Goes nice. Okay, let's look at this one next. Let's say find the general solution. Say y double prime plus 2y prime plus y equals 0. Okay, so you write down your characteristic equation. So that's r squared plus 2r plus 1 equals 0. Okay, so what that'd be, you factor it's r plus 1 equals 0. So we get basically r equals negative 1 here. Like that. Okay, so we have one solution here, right? Y sub 1 is equal to what? That'd be e to the negative 1x, like this. Okay, anything there so far? Now, the problem is, though, to find the general solution, we want to find all the solutions. Okay, this is a single solution here. We'll look for the general solution. We need a y sub 2 here, right? We only have one thing right here. Now, I need to find some other y sub 2 here, okay? It can't just be a constant of this. Like, for instance, you say, maybe I could write this. Maybe I can put a 5 here instead. You know, that's going to be a solution 2 to this if you multiply by a constant in front. That doesn't count. Okay, so you can't, not like this. Okay, so you can't do this one. On the handout, it mentioned that y sub 2 couldn't be like this. Okay, but we need some other solution here, right, to go here then. And once we have what's here, we got to find another one here. And once we can find one not like this, okay, then we can write down the general solution. Okay, so this is the next thing here. We got to find that y sub 2. Okay, basically, so let me say here, to find to find the general solution, need another solution. So we need to find our solution here. Okay. So basic ideas here. We'll see how this goes. So now you look for this. We'll try this out here. Look for, let's say, look for a solution like this. Y equals, say, u times e to the negative 1x. Kind of like what we did back in the first order ones. We'd substitute, put a, y equals u times something here, times some others. So basically you take u of x times some solution that's known already here, like that. So we're going to try to look for solutions like this now. Okay, so if I go back to the differential equation here, what we got is y double prime plus 2y prime plus y equals 0. And once we go through this one time here, we'll see kind of the form of it for the second one, what it will look like. But basically, we'll go through this now. So if I look for a solution like this here, I substitute that in here. So what that would be, well, now I can do my product rule. A little bit of a mess here. I got to take two derivatives here. Okay. I think this will just do one at a time. So I got the y, right? So I know y is equal to, write this down. We got y equals u e to the negative 1x. So y prime then would be what from the product rule? That would be right. Thanks. U prime. Yeah. Oh, I know what I was going to do here. I know what I did. So if I write this down, it's u prime e to the negative 1x plus, now you keep the first part, take derivative of the second part, like that. So that'd be u prime like this. Okay. Now u double prime, I'm going to show you something. I know I did this now. I want to show you this now. So u double prime, this is where it gets a bit of a mess, right? Because now what? Now you got to take derivative of this. So it's like a product rule here, product rule here. You see that now? Okay. But there is actually a way around this. There's kind of a shortcut for second derivatives using product rule. Let me show you this. There's kind of like a Pascal's triangle. When you expand a binomial, there's kind of a Pascal's triangle thing you can do, right? It kind of goes like, well, you have 1, 1, and then this is like for x. I don't know if you've seen this. It goes 1, 2, 1, and then 1, 3, 3, 1. Like for expanding a binomial, there's something called Pascal's triangle. Anyway, let me show you here. Basically, what you do, go back up to this one here for a minute. Take two derivatives of the first part. Okay, this like kind of expanding out by, it's like expanding out a binomial basically. So if you take two derivatives of the first part here, that'd be what? U double prime. So u double prime. You keep the second part just like it is. So it's like a product rule using second derivative. So you take u double prime, take two derivatives of the first part, keep the second part just like it is. Okay, plus now you put 2 here, 2 times. Now you take one derivative of each. Okay, so one derivative of each here now. So what, that'd be u prime, and a derivative here would be e to the negative 1x times negative 1. Okay, plus, now the last one here, now you keep the first part, keep the u, and now you take two derivatives of the second part. Okay, so what would be two derivatives of the second part here? If you got to think through it a bit. So two derivatives of the second part, e to the negative x, right? Because it kicks out a negative 1 each time. So it goes back e to the negative x. So e to the negative 1x. Okay, so it's kind of like a, so that's kind of a way to think of it there for a second derivative. Okay, if you're doing we'll never do a third derivative. If we do a third derivative, it'd be 1, 3, 3, 1. So you would take 3 derivatives of the first one, and then 2 derivatives, and then 1 derivative. It goes the other way then. Okay, but your coefficients would be 1, 3, 3, 3, 1. But anyway, that's a little bit faster. It's a bit faster than, you can get it directly from here, which is nice. You don't have to use this one to get the second derivative. It makes a mess. You can go through it, but you would get this. If you went through it all, you would get this here. Okay. So anyway, there's the derivatives there. So if I go back and sub in here now, so the y double prime, what that's according to what we got, u double prime e to the negative 1x plus 2u prime e to the negative 1x. Actually, it'd be a minus here now if I just do that, because that was a negative there. I want my second derivative plus u e to the negative 1x. So that's the second derivative plus 2 times the first derivative is from here. That's u prime e to the negative 1x minus u e to the negative 1x. Makes a mess here. Plus, now the y was this up here, u e to the negative 1x equals 0. Okay, anything there so far? Now, here's the nice thing that happens. There's actually a ton of canceling here. If you look at this, okay, actually, let me just read it out one more just to see it. I can distribute that 2 through. So I took that 2 through. And actually, if you look at this, it's kind of nice. I think it's nice. Maybe it's not. Is there canceling? Yeah, like here, this cancels with that. And then these two here, right? These two here will team up and go against this one. Okay, so those all cancel out there. Okay, so actually a whole bunch of canceling. This all goes away here. Okay, and you're just left with this then. U double prime e to the negative 1x equals 0, like that. Okay, so anything there? Well, the only way this can happen, this can never be 0 here. Okay, so the only way this happens is now, so that means u double prime has got to be 0. Okay, so that means u double prime has got to be 0 here, like that. Okay, so now we can learn about u here. Let's just do some antiderivatives. So that means u prime is what? U prime would be equal to a constant. Okay, call it c, for example. And then u single, and then u would finally be what here then? Cx, right? So you get Cx here. Okay, so, and by the way, we can let C be 1 here. I'll say here C equals 1 will suffice for this. Okay, so basically here, we got another solution here then, right? Y is equal to what? It was ux, or u e to negative 1x. So that would be x e to the negative 1x. Okay. So this is like our y sub 2 here. Now this is our other solution we got. Okay. So this is the second solution here then. Okay. So, right, the general solution. Okay. So the general solution is this then. We got, well, so I'll say y equals, now our first one was what? The y sub 1 was the e to the negative 1x. So I'd say c1 e to the negative 1x plus c sub 2. Their second solution was this, x e to the negative 1x is the general solution. Okay, so this is the general solution here then. So anything on that? Okay. Now it turns out here, there's nothing special about the negative 1. On ours we had, it was, right, our original solution was, we had e to the negative 1x. Nothing special at negative 1. If you put other number in there, okay, you would go through the same thing here, and the same sort of thing would happen. You get that same canceling. It looked a little different, but it would work out. You get all the same canceling there. Okay. So as a bottom line here, if you have repeated root, your second solution is this, you multiply it by x. Okay, so for the, so there's nothing special about r equal negative 1 with that. So I'll say here, nothing special about r equal negative 1 with that. That will always happen with this. And this thing here is always going to happen, right? So this will always happen when repeated, if you have repeated root. So that thing there always happen. So it's just going to be x out in front. Okay. Anything there? So for example, let's say find a general solution. Let's try this now. So we got y double prime minus 10y prime plus 25y equals 0. Okay, so I want to find the find the general solution here. First thing, write down the characteristic equation. Right, and so I get r minus 5 equals 0. So this is the repeated root situation. Okay, so we get r equal 5. So the general solution here then, we can just immediately write this now, right? Y equals C1 e to the 5x plus C2. What would be the rest of it here then? It's just like this now. Basically, if we did exactly what we did before, you can go through a whole thing. Okay, you find the same thing happen. Okay, so you don't do that every time. Okay, that is the general solution here. Okay, so anything on that? Okay, and again, you get two constants here when you do that because it's second order equation. And so, okay. All right, let's see here. Next then. Oh, let me turn the page there. Oh, okay. On to the next one here. Let's try this. Find general solution. So say y double prime plus 9y equals 0. So next up here. Okay. So find general solution here. So again, write down the characteristic equation. So what would that be here? What would be the equation? The characteristic equation with the r in it would be what here? Right, r squared plus 9, right? So r squared plus 9 equals 0. So you get this. Okay. Now, unfortunately here, right, if you go through this, if you factor, you get complex, you'll get imaginary numbers when you factor it. Okay. If it's r squared minus 9, it'd be pretty easy. But we got r squared plus 9. So let me do a couple of things here. If I go to quadratic formula, I'll just show you that, I guess. If I use quadratic formula to solve this, so would that be like -0 plus or minus square root of 0 squared minus 4 times a, which is 1 times c, which is 9, all over 2 times a, which is 1. You get here basically r equals plus or minus. That's going to be basically you get this is -36, right? So you get plus or minus square root of -36 all over 2, like that. So r equals plus or minus. Now square root of -36, you write that is 6i. Okay, got to do imaginary numbers here. 6i over 2. Okay, so r equals plus or minus 3i with this. Okay, so we got two values of r there, but they're imaginary numbers though. Okay, anything else so far on that? So our general solution here, according to it's actually going to be like this: y equals c1 e to the 3i plus c2 e to the -3i. Okay, is the general solution here. So. And this is actually an okay way to write the solution. You can write the solution like this actually, okay, but we really don't want to write it this way though. We don't want to have the imaginary numbers in it. Okay, so we need some way. We're going to try to figure out some way here to get rid of those imaginary numbers in this. So we just get like things like real value functions here instead. So these imaginary complex value ones. Okay, so we get this here. So now what from here? Okay, well, this goes back now. You can write some of this down if you like. We'll get to the answer here in a minute. But use what's here now. Back to Euler again, actually. There's one here called Euler's formula. Okay, I don't know if you guys have seen this before or not. Maybe you have, maybe you haven't. But it says this here. This is kind of an interesting thing. E to the I theta is equal to cosine theta plus I sine theta. I'll put this in the box here. Okay. This is actually kind of a very famous, it's a very celebrated result, this one here, but Euler's formula like this. So it actually relates, like the Euler number, the E here, okay, this number here, it relates it to, or it's like exponential there, relates it to like an angle and an imaginary number and then sine and cosine. So it has like all these kind of weird things related together here, like this. Okay, so this is called Euler's formula here. We're not going to use a whole lot in the course, actually, but you need it for this derivation part here. Okay, this is called Euler's formula. Okay, so for example, here then, if I apply Euler's formula, right, my solution reads like this then. So what? That'd be E to the I theta. So that would be, actually, if I think of the other way, it's like I should write as I3. Anyway, this thing here becomes like, I'm sorry, I lost an X in here somewhere, I think. It should be 3ix. There's X's up here on that. 3ix in those. I lost the X there on that. Okay, but anyway, if you apply Euler's formula here now, that'd be what? E to the I, here's the I, and then the theta is the 3x. The theta would be the 3x here. Okay, so it's cosine of 3x plus I sine of 3x, like that, close this parenthesis, plus c sub 2, okay, and then this would be what? Cosine of what here then? Yeah, negative 3x, okay, and cosine negative 3x, and then plus I sine of negative 3x, like this. You got this here. So anything there so far on that? So by Euler's formula, right, our general solution, which was this, you could rewrite like this. Now we're starting to get sines and cosines involved here a little bit. Now next thing you can do here, I don't want these really negatives over here for the negative 3x here. So you can do this. This is the next thing. We'll get to an answer in a minute. This is kind of derivation stuff. I'll have a box here in a minute at the end of this. You can just kind of watch this if you want, or write it down. It's up to you. Okay. Now this guy right here, cosine negative 3x. Cosine is an even function, right? If you look at like cosine wave, it looks the same on the right half as it does the left half if you graph it. It's an even function. Okay. Basically, cosine negative 3x is the same as cosine 3x, like this. Okay, it's a property of cosine. It's an even function, like that. Okay, it's a trigonometry thing there. And sine is an odd function, which means then basically it has the opposite sign on it. So basically, it goes like this: an odd function. Sine's odd, so you can write like this then. Okay, if you think about like a cosine wave real quick, just for example, cosine goes like this. Well, it's supposed to. You know, cosine looks like this if you graph it. Okay, so right, in other words, the value over here is the same as the value over here. So if I take negative 3x and replace it with 3x, it's the same result, right? Whether it's here or over here. And sine's odd function, right? That's like, so it's like sine wave goes like this. Okay, so here and over here, like if I pick number here, it's opposite signs, same magnitude, but opposite signs. Okay, so I can take negative 3x and put the minus in front there, like that. Okay, but anyway, here then, still looks like a mess. Okay, but now what you do here, if you pick judicious choices here for C1 and C2, Remember, this is the general solution, right? This is general solution, has all the solutions here. Okay, I can find some particular solutions if I pick values of the constants here. So if I choose, if you choose C1 equals C2 equals 1/2. If you choose C1 equals C2 equals 1/2, okay, what you'll find here, now think about if I put a half here for these. If I put a half here and a half here, if I distribute that then, I get like 1/2 cosine 3x here, and then I get like negative 1/2 of this. Okay, and then over here I get, again, 1/2 cosine 3x. If I distribute, I get a negative over here of this. This and this will cancel. If I put in a negative 1/2 for both C1 and C2 and distribute the 1/2 through, right, these two will zap out. These will zap out, and I'll get a 1/2 cosine 3x plus a 1/2 cosine 3x. A 1/2 plus 1/2 is 1. So basically, if you choose that, you get this solution here. Okay, if you choose this one here, let me say choosing this here, okay, comma after that, I get this solution here. Cosine 3x is a solution. Because this is the general solution. So all the solutions are here. If I choose C1, C2 is a 1/2, okay, this is one of the solutions here too, is cosine 3x. So that's a solution to it's out of the general solution here. Okay. Now another choice, this one's a little harder to see, but choosing, it turns out if you choose C1 equals negative 1/2 I and C2 equals 1/2 I, if you make these choices here, okay, I won't go through it, but, well, I kind of went away, but if you make those choices, make complex numbers here for these choices, okay, what happens here, I guess I'll show just in C1 here. If I take negative 1/2 I and distribute it, right, I get like a complex number here. Well, let's see. Yeah, okay. You can kind of see it. If I put in negative 1/2 I here and distribute, I get like negative 1/2 I cosine 3x here, and I get, and then over here, if I put in for the C2 1/2, I get 1/2 cosine, 1/2 I cosine 3x. So it'll cancel here. These two will cancel, right? If I put in negative 1/2 I. The other thing that happens too, if I put in negative 1/2 I here, what happens here? If I take, I'll have like an I times I then. What's I times I? I squared, which is what? I squared turns into, no, or, okay, if I should write this down here.
1.
I squared is equal to -1. Yeah, I squared is -1. Okay. Right, I squared is -1 there from the way complex numbers work. If you have an I squared turns into -1. So basically getting an I squared turns into -1 here. So you end up like a negative 1/2 I, or negative 1/2, and you get a positive 1/2 over here. These will cancel here then. Or actually, I said that wrong. These will cancel, and these will add. These will add together. Anyway, another solution you get here then is this. This is also a solution here. Okay. So if you make judicious choices for C1 and C2 here, okay, you get these two solutions here. This is a solution, and this is another solution. Okay. So I basically can call it Y1. I got a solution there. I get a different solution, Y2 here. Now, once I have two solutions here that are different, right, I got these two different solutions here now. So then I can rewrite the general solution. Okay. So the general solution can be written as this here now. Y equals C1 cosine 3x plus C2 sine 3x. Like this. You can write like this instead. So instead of the messy thing up here with the complex numbers, you could write the general solution like this. Like this one here then. Okay. So any questions in that one there? So for example, okay, this is the important thing in the box, or this part down here is the important part right here. So for example here, let's say it's taking our problem. Let's say we'll solve this now. Find a general solution. Okay, so let's say we have y double prime plus 25y equals 0, like this. So we'll find a general solution to this one. We don't have to go through that whole thing again here for this, but you find your characteristic equation, right? So you get r squared plus 5, basically plus 25 equals 0, right? Okay, so you get this here. And then your roots here then for this, it's going to be r equals 5i or r equals negative 5i. Those are the solutions there to the characteristic equation. Okay, so your general solution here then, you can just write like this now. It's C1 cosine 5x plus C2 sine 5x. Like that. Okay, so you end up with this here. What's that? As long as it's pure imaginary. Yeah, as long as it's pure imaginary. If it's a complex number, well, maybe I'll talk about this next time, but if it's like, say, this, okay, there's a little more to it. But yeah, that's right. So if it's just pure imaginary like this, if it's like it looks kind of like a difference, like a sum of squares thing or something like this, then yeah, that's your general solution. Because that'd be the general solution there. Okay. So anything on that one? Okay.
You have to go back up to the.
Yeah. Back up here. And by the way, you don't have to use quadratic formula for that either. Another way you could do that, so you write that part down there, or you could take this here. I'll just write it inside. You could say r squared equals -9, like this, and then basically you do something like this here. Take the square root on both sides, put a plus minus in front. Okay, so you get r equals plus or minus 3i, like that. That'd be an alternative to doing the formula. You could do that. Okay. Okay. So anything on that there so far? Okay. I guess maybe I'll save the third case for next. There's one more case to go, but maybe I'll let that go for next time. Yeah, I'll let that go for next time, I think. It'll give you something to look forward to for next time. So cliffhanger. So anyway, yeah, so you should be able to do some of the homework now, a little bit from this section, but this is not on the test. This won't be on the test, I don't think, next. And I'll get something posted probably by tomorrow. I'll get something posted for the test next Thursday. It might go through Euler's method. I might put it through Euler's method. Okay. But I didn't quite get through this, but this will probably save for next test. But I'll get something posted about the test in a few days here. But we'll finish this up next time, do some more stuff. And then next Tuesday, we'll do review for tests, and then we'll do tests Thursday next week. So, okay. I'll go ahead and stop there then.